When prints warp, most people immediately blame poor bed adhesion. We reach for glue sticks, liquid glue, slicer settings like brims, or anything that will keep the print planted on the build plate. While bed adhesion is an important factor in reducing warping, it is not the root cause why prints warp. You think PLA doesn't warp? Try printing it in a low ambient temperature with a lot of cooling and you'll see a nicely shaped smile instead of a flat bottom surface. Think infinite bed adhesion will give you big and flawless ASC prints? Nope, the layers can just split apart. So let's dive into this extremely important topic that most people misunderstand and end up blaming the wrong thing. To the naked eye, 3D printing appears to be a very simple process. We heat and extrude filament layer by layer until an object is formed. However, what happens to the molten plastic during the cooldown is a far more complex process that requires a deeper understanding at the microscopic level. To explain this as concisely and as simply as possible, I separate the cooldown process into two stages. The first is when the plastic cools from the printing temperature down to the glass transition temperature, also known as TG. This is not a single sharp point but a temperature range, and you can find this approximate value in the most filament datasheets. The second stage is when the plastic solidifies and continues cooling down towards the surrounding air or chamber temperature. Both stages affect warping in different ways. During the first stage, at a molecular level, polymer chains move quickly and then gradually slow down as the glass transition temperature is approached. At that point, the polymers for the most part lose their ability to move and rearrange. The reason why this is important is that the faster this cooldown process is, the more polymer chains get trapped in a higher stress state rather than a more neutral one. They become locked in with internal tension, commonly referred as residual stress. The surrounding air or chamber temperature, along with a part cooling fan, controls the print's cooldown speed. A hotter chamber and a lower part cooling mean the plastic spends more time in this solidifying phase. That results in lower residual stress inside the part and reduced potential for warping. Meanwhile, during the second stage, when the extruded plastic cools below the glass transition temperature, the print begins to shrink towards the surrounding air or chamber temperature. The further this temperature is from the material's glass transition temperature, the more the plastic will shrink. Because the print is a single object but does not cool evenly, instead cooling in sections, each additional layer increasingly pulls on the previous one due to shrinking forces. The larger the temperature difference between the glass transition temperature and the chamber temperature, the stronger these forces become. This leads to accumulating stress until either bed adhesion fails and print warps, or with materials like ASA, delamination can occur between the layers. To gather more testing data for this video, I upgraded my warping test jig with a stainless steel part that was manufactured by today's video sponsor, PCBWay. It acts as a flat and stable platform to attach overprinted parts and mount a dial indicator. The test sample gets clamped with a consistent force and we see the amount it warped, easy peasy. If you need anything similar made for your projects, make sure to check the variety of services PCBWay has to offer with a link in the video description. From all my testing, experience and research, there are 5 main ways to reduce warping. These include reducing the temperature difference between the material's glass transition temperature and the chamber temperature, using no part cooling or very minimal cooling, choosing materials that shrink less, selecting filaments with additives such as carbon or glass fibers, and finally increasing bed adhesion by using glue. However, things become much more complex when we compare materials with different polymer structures. For example, PTG, SA or polycarbonate have very different internal polymer chains than materials like PT, nylon or PPA. The first group of materials is called Amorphous, while the second group is called Semi-Crystalline. Polymer chains in amorphous materials always stay arranged like a bowl of noodles with no specific long-range order. Meanwhile, semi-crystalline materials can form very strong, tightly packed regions when the plastic stays between the melting temperature Tm and the glass transition temperature Tg. The more of these regions that form, the stronger, stiffer and the more heat resistant the part becomes. That is why annealing post-processing is crucial for semi-crystalline type of materials. By slowly heating the print, holding it for hours at elevated temperatures where polymers can rearrange, and then slowly cooling it down, we create conditions where more of those strong regions can form. Because of this, amorphous and semi-crystalline materials behave very differently as temperature increase. Amorphous materials like PTG, SA or polycarbonate lose almost all of their usable strength around the glass transition temperature. By contrast, semi-crystalline materials like PT, nylon or PPA still maintain a significant amount of strength above TG and only completely fail when those strong polymer regions break down at the melting temperature Tm. The true magic happens when we reinforce these semi-crystalline materials with carbon or glass fibers, which is why filaments are almost never sold without these additives. But what about PLA? PLA is an odd one. Technically it is semi-crystalline as it can form those strong regions during annealing, but throughout the regular printing process it behaves almost entirely like an amorphous polymer. So how do things differ when printing these more complex semi-crystalline materials? For amorphous materials like PLA, PTG, SA or polycarbonate, we want chamber temperatures that are not too far below their glass transition temperature. This ensures slower layer cooldown times and minimizes shrinkage. Meanwhile, for semi-crystalline materials like PT, nylon, PPA or PPS, we want the opposite. Chamber temperatures above the glass transition temperature, so that the more of those strong polymer regions can form during printing. The paradox is that these regions pack more densely and cause additional shrinkage, just like what happens during annealing. So while high chamber temperatures reduce internal stresses and produce stronger, stiffer and more heat-resistant parts, they can still increase warping depending on the material and part geometry. Achieving ideal chamber temperatures with PLA is easy since it has a low glass transition temperature of around 60 degrees Celsius, as seen with this bamboo basic PLA example. All plastics lose strength as temperature increases, and when we reach the heat deflection temperature or HDT, it essentially marks the end of a material's usable strength. This means we have to stay well below the HDT to ensure the entire print doesn't collapse or droop under its own weight. In the case of this basic PLA, with an HDT of 54 degrees Celsius, I wouldn't go above 45 degrees Celsius chamber temperature. But there is a catch. If you have tried printing PLA at 45 degrees Celsius chamber temperature, you have likely jammed your hot end. At that chamber temperature, the heatsink section of the hot end is simply not capable of dissipating the heat transferred from the much hotter heat block, which typically sits around 220 degrees Celsius. In the past, I tested how much force it takes to extrude this PLA filament through different hot ends. While it may not seem like much, a force of 1.5 kilograms translates to roughly 6 megapascals on the filament's cross-section. This is about 3 times higher than the value listed in the datasheet at 54 degrees Celsius. As a result, the filament begins to deform under the extrusion force, expand, and ultimately jam the hot end. The reason we never see clogs when printing filaments like SA or polycarbonate is that consumer-grade printers are typically limited to chamber temperatures of around 65 degrees Celsius, which is not high enough to cause jamming in most hot ends. Printers designed for professional ASA, polycarbonate, nylon or even peak printing operates at much higher chamber temperatures. This doesn't mean we can't print most of these materials on our consumer-grade machines. It simply means our prints cannot be as large or as thick. Larger and thicker parts generate stronger shrinkage forces, especially at lower chamber temperatures, which leads to increased warping and higher residual stresses within the part. So before printing one of these more advanced materials, make sure your printer is capable of reaching high chamber temperatures rather than simply adding a third layer of glue. Chamber heaters not only help preheat quickly and maintain high chamber temperatures, but also circulate air within the chamber. This prevents cold zones from forming and eliminates drafts of cooler air hitting the print as hot air rises from the bed. Using as little part cooling as possible is also key. The difference between active and passive cooling is enormous with CPU coolers, and the same applies to actively cooling the print. If layer times are long and there is no steep overhangs, part cooling may not be needed at all. This doesn't mean you can get away with a greasy build plate. It still needs to be washed with at least a dish soap, and a bed adhesive should be used for materials like nylons that don't naturally bond well to PI plates. It almost never hurts to have more bed adhesion. Just don't try to compensate for insufficient chamber temperatures and excessive cooling by increasing bed adhesion alone. When it comes to the models themselves, rounded corners lead to more even cooldown. Nobody bakes square pizzas because the corners would burn. 3D printing follows the same principle, just in the opposite direction. Even infill patterns matter. Gyroid infill can stretch more, while triangular or grid patterns cannot. As a result, they pull on the outer walls more strongly, increasing the potential for warping. Finally, once the print finishes, it is always better to let it cool down to room temperature before removing it. If you just cannot wait for that, at least wait until the heat bed cools down well below the TG of the material you used to make the print, because the bottom layers will still be very hot, and bending the build plate too early can permanently deform the part. I put a lot of work into this video, so if you know those people who constantly post warped prints on Reddit, feel free to send it their way. Jokes aside, I hope this, as complete as possible, explanation of why prints actually warp was helpful, and if you have any questions or suggestions, please let me know. Huge thanks to everyone who supports my work on YouTube and Patreon. Well, that's all for me, and we'll see you next time.